All right, so we've gotten through the basic command injection and the simple buffer overflows, and now I want to talk about 203 and 204. 203 is the next step. Now, we did a buffer overflow where you could just leak into the next variable back in 201, and the next variable happened to be used to execute a command, but that was kind of contrived. In 202, we redirected execution to code that the developer put there, but we didn't inject any code of our own. So that might seem like a less powerful exploit, but it turns out that is in fact the exploit that is most commonly used these days, called return-oriented programming, because of defenses. Defenses make it very hard to inject your own code. So the way most attacks are now done is by reusing code that the developer put there. But in between, this was the one that was considered the most powerful. When buffer overflows first started becoming popular, back with the original article in Frac from Aleph Null, is where you inject your own code. So here, what we're going to do is have a vulnerable program here, and you just download this thing, and you can look at the source code. Let's look at it here, ev3a.c. All right, so this has a main routine here, and it has a usage message to tell you if you don't give it a parameter. And if you do give it a parameter, then it just prints the stack pointer, and it's done, but it calls this function copier. And copier is what gets the stack pointer. So this gets the stack pointer, and then it does a string copy of the buffer that came in the command line argument into a string variable that is 1,000 bytes large. So we have a buffer overflow here because the command line variable could be of any length, and it goes into something that's only got room for 1,000. So there's a simple buffer overflow, and there is a lot of room this time, 1,000 bytes. Before we had just 10 or 50 bytes. And the reason is because we need some room to put in code, and you can't really put in code that does much of anything without a few hundred bytes to inject typically, although people who try really hard can get some very simple shell code down to like 40 or 50 bytes, but for normal things, you need like 200 or so. So we need to make a fuzzer. Well, first, let's see this thing work. ed3a, and it wants a string, so if I say hello, it just works. But if this string was much longer, like longer than 1,000, then it would crash. So rather than try to figure out how to type 1,000 at the command line, I'm going to make a fuzzer. So I did that here. And this is Python. By the way, I'm using the old version of Python, which is now deprecated. I'm just too lazy to update my stuff right now. The main difference if you have the new version is you got to put parentheses around the print. Anyway, so this takes a command line argument for the length, and it prints that many A's. So I can do fuzzer 10, and it prints 10 A's, so I can do fuzzer 100, and it prints 100 A's, so that's very convenient. So let's fuzz the program. We can do ed3a, and the dollars parentheses tells bash to execute this command and then put the results in the command line. So that will feed in 100 A's, and that'll feed in 1,000 A's, and that'll feed in 1,020 A's, and now I get a segmentation fault. So I know that I need to put in something in the range of 1,020 to cause a crash, and I need to look at it in a debugger to figure out exactly which of those additional 20 characters ended up in the instruction pointer. So we've done this before. We used the GNU debugger in quiet mode on ed3a, and now we run, oops, got to spell it right. I'll just leave and come back, ed3a. Okay, now we run with $fuzzer, oops, 1020. And you see, in fact, some of my A's made it into the instruction pointer. You see it right there, 41, 41, 41, 41. So that's pretty good. All right, so I have an overflow. And in order to tell exactly which characters got in there, I have to do something smarter than just make a dumb fuzzer. So I make this. Now I'm going to put in a pattern. I put in 1,000 A's, and then I put in B, 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 C, 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 D, 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 E, 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 so that if it was some of those first 20 characters that ended up in the instruction pointer, I'll find it. And I think that's true because some of the A's got there, and there's the same input, 1,020. So I just need to run that in the debugger with EX1. So I go back to the debugger, run, not fuzzer, but EX1. Okay, and what have I done wrong? ED3A. All right. Something is spectacularly wrong with my EX1. Maybe I forgot to make it executable or something. Let's get out of here and see if I can run EX1. Oh, I can't. Okay, so catch EX1. Ah, I got an extra blank line at the top. This will happen if you have a blank line at the top, the shebang line has to be the first line or it won't work. So now let's see if that did it. And it did it. Okay, now EX1 prints 1,000 A's and then B's, C's, D's, and so on. Okay, so now I can go in the debugger. I can run, taking the data from the output of the command EX1. And now I can see it's 45, 45, 45, 45. So it's A, B, C, D, E. It's the E's right here that ended up in the instruction pointer. So now I can control the instruction pointer. Okay. Now I need to have shellcode. Now, if you read the Shellcoder's Handbook, they'll actually talk about how to write shellcode in C, compile it, and then clean up your assembly language to get rid of the null bytes and such. And that's cool if you want to do that. And in fact, when you get to the ARM exploits, you really have to do that because as far as I can tell, there is no Metasploit for ARM. Although now there is some ARM attacks in Metasploit. I haven't been able to make shellcode with MSF Venom, but you can totally make x86 and x64 shellcode with Metasploit, and that's what I always do. So you can install Metasploit, this curl command, and these commands will install Metasploit on Linux, and then you can use MSF Venom. And MSF Venom makes Metasploit payloads, which are very powerful and very handy, but of course, antivirus will catch them. But we're not going to worry about that right now. So here you can look at Linux payloads that bind to a TCP port to make a listening shell of some sort, and there's quite a few of them. And it turns out the easiest one to use is this one, Linux x86 shell bind TCP. That will just listen on port 4444 and let you connect from anywhere and control the machine. Now, this is the simplest payload to use. It's also not much value in a practical pen test because any company that is not complete idiots will have a firewall at least that doesn't let traffic come in on strange ports like 4444. So if you manage to make a process listen on a port like that, you won't be able to connect to it from outside the firewall. So a reverse shell is more practical in practice, but for what we're doing here, we just want to see how to inject it in memory, so we'll just choose the simplest possible exploit. So if you run this command, and you need sudo to run it on these Debian machines for some reason, this will start listening on port 31337, and it gives you Python code. But if you run it like this, you'll see a null byte in the Python code. And the problem here is we are injecting into a string variable. We saw this, the C source code reserved 1,000 byte string variable, and nulls terminate string variables in C. So if you try to inject a string containing this code, it won't all go into memory. It'll only read the part up to the first null and put that in memory, and the rest of it will be ignored. So you can't have any null bytes in your exploit code, or to be more careful, you can only have one null byte, and it has to be the last byte, which, by the way, is what happened when we injected some null bytes in a 64-bit exploit in the last video. I didn't mention it, but we did in fact have a string there with some nulls at the end, and only the first null went in, but the other null was not really necessary. So you can avoid null bytes. You can add this -b \x00 switch to avoid null characters, but there might be other characters that also break strings in input like space and tab and carriage return and line feed. So if you have plenty of room, you can just avoid everything by using a simple pattern in Metasploit like alpha mixed. This will use just letters and numbers, no fancy characters at all. The only penalty of that is it makes your exploit bigger, because it has to be encoded. So this was 382 bytes. And when you make it this way, it's going to be 230 bytes. Let me point to the actual, this one is 78 bytes of actual binary, but that's 382 bytes of Python, because each binary byte takes about 4 or 5 characters in Python, \x53, and then you've got some extra overhead here. So the number that matters to us is 78 bytes in memory. And this one, using letters, is now 231 bytes in memory, which is fine, because remember, we have 1,000 bytes we're injecting. We have plenty of room to put in something that's 230 bytes long. So that's what I did. And so that's EX2. Let's take a look at that. Let's catch EX2. All right, so what this is just a shebang line and a blank line, then all the code that came from Python. And you can notice these are all printable characters, like 43 and 61. All these are all uppercase, lowercase, and numbers. Nothing else is used. Then I'm going to have a NOP sled, which we haven't talked about, but we need to talk about. So you put in this 230 bytes. And when you make your attack, you put in a NOP sled, which is just a bunch of these 90 bytes, which do nothing, but they're important for your attack, as we'll see. Then you put in the buff, which is what they call the egg. That is the code I'm trying to inject. Then I put in a suffix, which is calculated to be enough bytes to get me to where the EIP is. And then I put in an EIP. This is going to control the instruction pointer, and I don't know what value to put in there, so I just put in a dummy value of 1, 2, 3, 4 for now. So if I run this thing, which is EX2, here's what it looks like. It has a bunch of NOPs. That's what these question marks are. Then it has the egg, which is all these random characters, which is the Metasploit payload, which in fact is using printable characters this time. And then I have a bunch of extra A's at the end just to pad it to the right length. And then I have 1, 2, 3, 4, which, if everything has gone correctly, is going to go into the instruction pointer. So we can test that in the debugger. So let's go to GDB in quiet mode again, ED3A. All right. And I'm going to disassemble copier. All right. And the point is here, I don't have source code for this one. So I'm going to have to disassemble at the assembly language instruction. Now here's the copier routine, and here's a rule for extremely useful in reverse engineering. Almost all your tools give you far too much information, and they fill the screen with baffling nonsense. And the secret is all the easy stuff is on the right and usually at the bottom, because beginners look at the easy stuff. Experts want to focus on the complicated stuff. So when you see a screen full of somewhat mind-boggling stuff like this, look on the right and you'll see familiar looking stuff like C. Here's the string copy command. And if you remember our source code, let me go back and bring it up. There's the source code of this program. This program has a main routine, and then it has a copier, and the copier uses string copy to put a string into a buffer that's only 1,000 big. This is where the overflow occurs. And this return is where the crash will happen if I've corrupted the memory through the overflow. So the string copy is the command that causes the overflow, and a single call, string copy buffer string in assembly code, is actually all of this stuff, because it's a lot of this stuff. What it does is it pushes some arguments onto the stack, and then it calls this. So it's probably this much anyway, is all the preparation. That push might be part of it too. Anyway, this is when it actually calls the string copy routine. So I would like to let that happen, so it causes the overflow, and then break here so I can examine what the stack looks like after the overflow. So this is the address I want to stop at. And let me go down to my instructions again. Okay, 241, 241. Okay, so that's the address I want to break at. So this is the command to break there. Break star and then the hexadecimal address. This is how you break when you do not have access to source code lines. You can break at an assembly code line. So now I can run and take my data from my input of EX2, and it's going to hit the break, and now I can examine the stack. So I do info registers, just like we did before, and I look for ESP and EBP. The stack goes from CE50 to D258. It's much bigger now. The stack is big enough to store 1,000 bytes and a few more. So I want to remember this number, D258. And now I think I'll do X410 is what I did. That'll do it. 410X ESP. So D258 is going to show it to me in pages. So I press enter a few times. Now here is D250. This is D258. So the stack frame goes back from that point all the way back to here. Remember, this is the way I like to do it. I highlight the stack frame, and then right after that, I'll see the EIP. So the first thing I notice is this is 258, this is 250, 254, 258, and this is 25C. And here I see 1, 2, 3, 4. 41 is capital A, 31 is the digit 1. Those are very handy things to know. So this is the ASCII 1, 2, 3, 4. And that's what I put in my code. So the first thing I observe is that I have succeeded in targeting the EIP. I put in a fake value, of course, that's just going to cause a crash because I don't know what value to put in there yet. And now I can go back in the stack and see what I've done. Here is where my variable started entering the stack, and I have a whole lot of 90s. And down here is the code I want to execute. All this stuff is the Metasploit shellcode. So I could try to jump exactly to where it starts, which is here. And if I succeed in that, that'll work. But in practice, you often make errors. You might make a mistake. The target system you're attacking might not be exactly equal to the machine you're developing your attack on. And here's something even more cruel and horrible. GDB is not very accurate. GDB is often wrong by up to 50 or 80 bytes in the addresses of things, because the environment it creates in the debugger is not exactly equal to the real environment in which it runs. And I've read pages trying to explain the difference. I don't really understand exactly why. It seems to be a much larger difference than it should be. But in practice, my students had great suffering with this, so I learned to just use a NOP sled. This is why everybody uses a NOP sled. 90 is the command that does nothing, NOP. So instead of jumping right to your injection, you jump into the middle of this sled. And now you can be wrong by like 100 bytes either way, and it'll still work. As long as you actually hit any part of the NOP sled, it will just do NOP, 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 and slide down the sled and run the egg. So you don't go here. If you want to avoid great suffering, you just pick some place back in the middle. The only thing is you cannot choose a byte that contains 0. If you do, you'll be trying to inject that address and it'll break your shellcode. So you choose some address back there. And here I used CF50, which is this one, which is fine. You could pretty much pick any of them. All right, so that's the address to inject. And so that tells me how to complete the exploit. So now it's going to be called EX3. Let me get out of the debugger. And let's see if I put in EX3. I think I did. Looks like I didn't. All right, I'm going to do it here. I'm going to copy. Oh, I'm in the wrong directory? I am in the wrong directory. Huh. Can't be. All right, nope. I just didn't put it in. EX2 to EX3. Okay. Nano EX3. All right. This is my exploit, and all I have to do is insert that address like that. So I'm going to go down here, and instead of putting in 1, 2, 3, 4, I put in \x50 CF. Okay, if I've done that correctly, that is an address that will hit the NOP sled. So let's GDB it again. There we go. And let's run X3. And notice it starts the program and it does not crash. It just freezes. Now that's pretty awesome. That's happening because it worked. And to see that it worked, I need a second shell. So I go back to my Google Cloud platform and I hit SSH a second time. This shell is still running and it's going to open a second shell onto my same server. This is why I love Google Cloud. It is very wonderful, very easy to use. And in here, I should be able to use SSPant to see what I've got. So let's see. Okay. If I do SS minus pant, this will show me the socket state of all my network connections. And someplace up here, I will see it listening on 31337. So this program, ED3A, is listening on port 31337. And so I can connect. And by the way, I could connect from anywhere, but I think I'll just do it locally. So netcat locally 127.0.0.1 on 31337. Now I've got a connection. See, here it is, that launch dash. Now I can execute commands here like who am I, and date, and ls, and so on. You've now got command injection. You've got a listening shell. You're running the code you injected. This is the classic Aleph null buffer overflow exploit, where you inject code and run it, and you can run anything that you can write in assembly code that will fit into the room you have to inject. So it's pretty awesome, but it only works if you don't have the modern defenses turned on, which people have often. Anyway, so I'm going to quit the debugger. All right, and so there's a remote server you can exploit here and get in there, and some tips here, and a couple of remote servers you can attack with that technique. All right. And format strings are quite a bit different. I think I'm going to stop now and make it a separate lecture to talk about format strings. So I'm going to stop the recording.